Hey, I'm Diabeticus. Welcome to episode 4. To recap, we use the general equation of a normal line to find the intersection of two closed normal lines on x cubed. Then, we generalize that process and got ourselves two extremely complex equations of x and y with a lot of roots on it. But by taking the limit as the second normal line approaches the first, we ultimately made them simpler, giving us the parameter 1 half apple minus 9 halves apple to the fifth, 5 halves apple cubed plus 1 over 6 apple. That locates the POI of seemingly only one normal line of any value of apple, which is legal. Moreover, if any value of apple on this parameter sits on the cone of the normal map of x cubed, then all values of apple draws the cone itself. Now, in this episode, we will use our acquired parameter as a means to ultimately locate the pseudo-foci of our dear friend x cubed. To begin, let's understand how the parameter works by separating it into two separate x and y equations and changing the apples to put to the correct variables, where we have y equals 5 halves x cubed plus 1 over 6x, and similarly x equals 1 halves y minus 9 halves 9 to the fifth. By graphing these two equations, we get a visible comparison to them and the cone. And if the x equation is giving you some mathematical anxiety, we'll ignore it temporarily, leaving us with the y component and the cone. Now observe that the y component is just the y behavior of the cone, which also means this and the cone basically have the same range. So wherever the y component meets a higher low, the cone meets a higher low. From this information, we can assume that the y value of the pseudo-foci are the minimum and maximum of the y component. And oh boy, didn't I say minimum and maximum because it's calculus time. Now, it may be tricky here to assume what's minimum and maximum based on what these words would mean, but for now, let's just say that on the right side, the graph has a local minimum, and on the left, the graph has a local maximum. So what precisely are these local maximum and minimum? Well, they are y values that may be the lowest or highest point on the graph, but the important characteristic of these values is that the slope of that value is generally 0, where it's that good part of the roller coaster ride. Since at these values the slope is 0, the derivative must be 0 at that point too. So by taking the derivative of the y component and equating it to 0, we are looking for the moment when that good part of the roller coaster ride happens on the y component. Now let's take the derivative of the y component, and to do that, we multiply the term by its power and reduce the exponent by 1, like on the second episode. The second term has a power of -1, so we get 15 halves x squared minus 1 over 6x squared. This equation is our derivative, so we then equate it to 0 and solve for x. Firstly, transfer the second term to the right for equality. Then multiply both sides by 6x squared to cancel the right x. After that, we divide both sides by 45, leaving only an x to the fourth term on the left. Next, we take the fourth root of both sides to get x only, giving us the fourth root of 1 over 45. Since it's the fourth root, our answer must have a plus-minus sign, because the negative, the fourth power, is also positive. So overall, we have plus minus fourth root of 1 over 45. So what does this number mean? Well, they're the x values of the y component where both the local minimum and maximum take place. Remember that we need the y value of these minimum and maximum. So if we plug the positive answer to our y component, we get 5 halves, fourth root of 1 over 45 cubed, plus 1 over 6 times the fourth root of 1 over 45. And if we entrust our mighty well, actually, no. We don't want to estimate this because we want the precise location of the pseudo-foci. So to do this, let's sort of undo this step by substituting the fourth root of 1 over 45 into u. Not me, u. Letter u. So next we multiply the first term by 6u over 6u, giving us 15u to the fourth plus 1 all over 6u. Now, notice that we have a u to the fourth. U is the fourth root of 1 over 45, which means the power and root cancel out, leaving only 1 over 45. Now, the 15 and 1 over 45 simplify to 1 over 3. Adding 1, we have 4 over 3 over 6u. Last thing, since u has a 1 over 45, we can actually flip this to 45 to the numerator, with still a fourth root. Simplifying further, we have our y solution, 2/9 fourth root of 45. But we ain't done yet. We still have our negative x value to plug y to. But do we really need to? The odd function behavior of x cubed seems to also apply to the cone graph, which means the pseudo-foci have equal y distance from the x-axis. Overall, I'm saying that the other y value from the other pseudo-focus is simply negative 2/9 fourth root of 45, because, well, the x is negative. Okay, we got ourselves the y values of the cones. Now we do the same long process for getting the x, right? Nope, not really. Plugging fourth root of 1 over 45 to the x variable of the y component to get 2/9 fourth root of 45 is the same thing as plugging fourth root 1 over 45 to the apple variable of the y part of the parameter to get the same answer. And since x also depends on the value of apple, we can use that same number to get the x part of the parameter. So our equation of x is 1/2 apple minus 9/2 apple to the fifth. And if we plug the fourth root directly, we could just use the calculator to estimate, but no, we want an exact form for our pseudo-focus. So firstly, let's apple a 1/2 apple, giving us 1/2 apple times 1 minus 9 apple to the fourth. Secondly, we know apple to the fourth cancels out the fourth root if we plug it in. So plugging the apple, we get 1/2 apple times 1 minus 9 45ths. 9 45ths simplifies to 1/5, so subtracting that to 1, we get 4/5. Dividing the two, we have 2/5 apple. Since we don't have anything else to do, we plug the apple value, giving 2/5 fourth root of 1 over 45. That is the first x value. The second x value is easy enough. Since our cones are odd like x cubed, the second x value is most intuitively negative 2/5 fourth root of 1 over 45. Now all we have to do is express all our x and y values as coordinates. Since our right pseudo-focus is on the first quadrant, this point must be 2/5 fourth root of 1 over 45 and 2/9 fourth root of 45. Likewise, the other pseudo-focus is on the third quadrant, so this guy is negative 2/5 fourth root of 1 over 45 and negative 2/9 fourth root of 45. Boom! Finally, we have found ourselves pseudo-foci of x cubed. Amazing. Prodigious. But there's still something left to clarify. So what does the apple value fourth root of 1 over 45 mean in terms of all we've learned so far? To start off, the apples in the parameter are originally the x value used to find the equation of a normal line on x cubed. And with apple as the fourth root number, we have a normal line crossing the point on fourth root of 1 over 45 and fourth root of 1 over 45 cubed. And now, if we draw an infinitesimally close normal line to it, then the two normal lines intersect at a coordinate defined by the x value apple. And this intersection point is what ultimately turns out to be the pseudo-focus. In formal, abstract diction, this is the significance of fourth root of 1 over 45. There exists a normal line that crosses perpendicularly to the function x cubed on the point a cubed, in relation to a, such that an infinitesimally close normal line intersects the first, where the point of intersection is the lower bound of a range of a set of all other intersections from pairs of closed normal lines that intersect the function from 0, x, infinity. And a is the fourth root of 1 over 45. And so, we are finally done. We have found the pseudo-focus, and it only took us 4 episodes to finally find it. Because everyone watching can take a break now and fully forget about it, right? Right? Nope. Okay, see you next video. Bye bye.